We'll begin our discussion on derivatives today. What is a derivative? We see the graph of the function y equals x squared. Notice I've marked the point 2, 4. And I've drawn a tangent line to that point. The tangent line at a given point is simply the straight line that just touches the curve at that point. We know from our previous studies that about slope in lines, that a line has a constant slope. The derivative of a function gives us the slope of the tangent line. In this case, the derivative is denoted y prime. In general, for any function f of x, the derivative of f of x, denoted f prime of x, gives us two things. Number one, the slope of the tangent line. Two, the instantaneous rate of change of the function. These are basically equivalent. Understand the instantaneous rate of change is simply the measure of the slope of the tangent line at that point, or how quickly the function is changing at that point. Let's look at some simple cases. For a linear function, f of x equals mx plus b. By definition, our derivative, f prime of x, is equal to m. This should make sense, because a tangent to any point on this line is simply the line itself, and the derivative gives us the slope of the tangent line. What about a constant function, f of x equals b? In this case, f prime of x equals 0. This should make sense also, because any tangent line to this function is just the line itself. And the slope of this line is always 0. Remember, the derivative gives us the slope of the tangent line. Please note, the derivative of any constant function is always 0. Let's get into a slightly more complex function, f of x equals x squared. In this case, the derivative is f prime of x equals 2x. Notice how the derivative is not constant but has a variable in it. Why is this? Let's change screens and look at an online simulator. Notice that I have both the graph of the function and the graph of the tangent line. Notice how when I move the point I'm looking for to the left of 0, the slope of the tangent line is negative. When I move the point to 0, the slope of the tangent line is 0. Notice how when I move the point I'm looking for to the right of 0, the slope of the tangent line is positive. This corresponds to our function f prime of x equals 2x. If we plug in a number to the left of 0, the derivative is negative. 2 times negative is negative. If we plug in 0, the derivative is 0. 2 times 0 is 0. If we plug in a number to the right of 0, the derivative is positive. 2 times positive is positive. These all correspond to the way our tangent line behaves. Let's look at one more function, f of x equals x cubed. In this case, our derivative is f prime of x equals 3x squared. Let's look at another applet. Looking at another applet, we see how our tangent line always has a positive slope until it hits x equals 0, and the slope of the tangent line is 0. This again corresponds to our first derivative function, where 3x squared is always positive except for when x is 0 and 3x squared is 0. Let's develop what we'll call the power rule. Let r be any number. For a given function, f of x equals x to the r. Its derivative is f prime of x equals f prime of x equals r, x to the r minus 1. we simply bring the number from the exponent down in front of our variable and subtract 1 from our exponent. This follows the patterns we already saw for quadratics, where f of x equals x squared, where the derivative f prime of x equals 2x, and cubics, where f of x equals x cubed, where f prime of x equals 3x squared. Let's practice some. Calculate the derivatives for the following. You may want to pause the video here and work some of these out on your own. What is the derivative of f of x equals x to the fifth? It's simply f prime of x equals 5x to the fourth. Notice how we brought the 5 down and subtracted 1. What is the derivative of f of x equals x to the 12th? It's f prime of x equals 12x to the 11th. Again, we brought the 12 down and subtracted 1. What is the derivative of f of x equals x to the negative 6? It's f prime of x is negative 6, x to the negative 7. Again, we're subtracting negative numbers, so negative 6 minus 1 is negative 7. What is the derivative of f of x equals x to the 4th, x to the 4/3? It's f prime of x is 4/3 x to the 1/3. Again, we're dealing with fractions, so you may take a little while to master that. Let's try a few more. Again, feel free to pause and work through these. For our first one, f of x equals 1 over x. We will rewrite it as x to the negative 1, so we can apply our power rule. The derivative is f prime of x is negative 1, x to the negative 1, 2. And we can rewrite our final answer as negative 1 over x squared. For number 2, we can rewrite the problem again as, instead of f of x equals the square root of x, this equals x to the 1/2. Our derivative is f prime of x equals 1/2 x to the negative 1/2. And we rewrite this final answer as 1/2 1 over 2 root x. What's the derivative of f of x equals x to the 2/3? It's simply f prime of x is 2/3 x to the negative 1/3. Again, following the same pattern. And what is the derivative of f of x is x to the negative 4/3? It is f prime of x equals negative 4/3 x to the 7/3. X to the negative 7/3, I apologize. I will get that fixed. Let's find the derivatives for the following at the given points. Our first example is f of x equals x to the fifth at x equals 2. We already know f prime of x is 5x to the 4th. So evaluating our derivative of x equals 2, we get f prime of 2 equals 5. Instead of x, we have 2 to the 4th. 2 to the 4th is 16 times 5 is 80. I encourage you to take a moment, pause the video, and practice on the next 3. Again, we're just taking the derivative and then plugging in for x. Let's expand our concept now. Find the equation of the tangent line to f of x equals x squared at x equals 3. We want to find an equation for a line. We ask ourselves, do we have a point? No. And do we have a slope? No. We are given the x value, and we can plug into the function to get a y value. F of 3 equals 3 squared, which is 9. This is the point, 3, 9. Also, we're given a function, and we know that the derivative of a function gives us the slope of the tangent line. So f prime of x is 2x, which means that f prime to 3 is 6. Now we have a slope and a point, so we can plug into the point-slope form. We can choose the point we're given. Y minus y1 equals m times x minus x1. In this case, y minus 9 equals 6 times x minus 3. Let's look at another one. Find the equation of the line to f of x equals the square root of x at x equals 1/4. We ask ourselves, do we have a point? No. And do we have a slope? No. Again, we are given an x value. We can plug in the function to get the y value. F of 1/4 equals the square root of 1/4, which is 1/2. So the point is 1/4, comma 1/2. We are given a function as well, and we know the derivative of the function gives us the slope of the tangent line. We actually took the derivative of f of x equals the square root of x in a prior slide. It was f prime of x equals 1 over 2 root x. So f prime to 1/4 is 1 over 2. Square root of 1/4 is 1/2. 2 times 1/2 is 1. So this is simply equal to 1. Now we have a slope and a point, so we can plug into the point slope form. Y minus y1 is m times x minus x1. This gives us y minus 1/2 is 1 times x minus 1/4. Let's look at more general rules for derivative. There's something called the constant multiple rule. This d by dx means derivative. The d by dx of k times f of x equals k times d by dx of f of x. Basically, we can just pull the constant out front. This k gets pulled out front and take the derivative of the function itself. Your sum rule says d by dx of f of x plus g of x equals d by dx of f of x plus d by dx of g of x. Basically, we can split our individual functions that are separated by plus and minus signs and just take their derivatives individually. Let's look at some examples. For the function f of x equals 8x to the 5th. This is an example of a constant multiple rule. We simply ignore the 8 by pulling it out front and taking the derivative of x to the 5th. F prime of x equals 8. The derivative of x to the 5th is 5x to the 4th, which equals 40x to the 4th. Notice how we have to simplify our answer by multiplying the 8 and the 5. For an example of a sum rule, we have f of x equals x to the 12th plus x to the 9th. We're simply going to take the derivative of each term separately. Remember, the terms are separated by plus and minus signs. This gives us f prime of x. Derivative of x to the 12th is 12x to the 11th, and the derivative of x to the 9th is 9x to the 8th. Let's now combine the constant multiple and sum rules into a single problem. We have f of x is 3x to the negative 6 minus x cubed. Our derivative is f prime of x is negative 18x to the negative 7 minus 3x squared. Notice how we took the derivative of each term separately and ignored the coefficients while doing the actual derivative. Let's look at one last example. F of x equals 6x to the 4/3 minus x squared plus 8. Although this has 3 terms in it, we treat each term separately just as our sum property tells us to. F prime of x equals 8x to the 1/3 minus 2x. Please note, I don't want to gloss over this, but we mentioned it earlier, and the derivative of a constant term is simply 0. Please pause the video here and work through a few more examples. Hit play when you're ready to check your work. I apologize, the last two are the same problems as before. Since the derivative function is also a function, we should be able to take the derivative of it. The second derivative function, f of x, is simply the derivative of the first derivative. Let's look at the function f of x equals x squared. We know how to take its derivative. F primed of x equals 2x. We can now take the derivative of f primed. We denote the second derivative as f double primed. It is simply the derivative of the first derivative. The derivative of 2x is simply f double primed of x is equal to 2. Let's pause the video here and let you work through a few more examples. Hit play when you're ready to work. Check your work. What if we're not always raising just x to a power? We have what is known as a general power rule. d by dx of g of x to the r power equals r g of x to the r minus 1 times g primed of x. In this case, we're raising g of x to the power r, and we want to take its derivative. That is what the notation d by dx stands for. We do the same thing as before. We bring the r down and subtract 1 from it to make the new exponent. However, we do a couple other things. We leave the g of x alone inside our brackets, but we multiply our answer by the derivative of g of x, which is g primed of x. Let's look at an example. F of x equals x to the fourth minus x squared, all to the seventh power. Remember, our rule states the following for the derivative. Derivative g of x to the r power. We bring down our r, g of x to the r minus 1 times g primed of x. We take the derivative of the outside exponent. This gives us 7 x to the fourth, 7 times the quantity x to the fourth minus x squared to the sixth power. But we now have to multiply that answer by the derivative of what is inside. This is just the derivative of the outside right now. The derivative of g to the x, the stuff inside, and the derivative of x to the fourth minus x squared, is 4x cubed minus 2x. This is actually an introduction to chain rule, which we'll get more into later. Let's look at a concept called marginal cost. If c of x is a cost function, please note that this is important to pay attention to because we will carry this concept forward and also study marginal revenue and marginal profit. By definition, if c of x is a cost function, then the marginal cost is c primed of x. The marginal cost of producing a units, c primed of a, is approximately equal to c of a minus c of a plus 1 minus c of a, which is the additional cost that is incurred when the production level is increased by 1 unit from a to a plus 1. Our formula is c primed of a is approximately equal to c of a plus 1 minus c of a. If you want to think of c primed of a as the slope of the tangent line at point A, then a good estimate for this slope is to calculate the slope between the points a and a plus 1. This slope would give us our change in y, which would be c of a plus 1 minus c of a, which is what we have here, and our change of x would be a plus 1 minus a, which simply equals 1 because the a's cancel. Hence the reason our right hand side is equal to just c of a plus 1 minus c of a, and gives us a good approximation for c primed of a. Let's look at an example of this. Let c of x be the cost in dollars of manufacturing x iPads per day in a certain factory. If c of 40 equals 5,000 and c primed of 40 equals 45, estimate the cost of manufacturing 41 iPads per day. What is the marginal cost of producing the 41st iPad? By definition, the marginal cost gives us the additional cost that is incurred when the production level is increased by 1 unit from a to a plus 1. We're actually given this in the problem. C primed of 40 equals 45. In other words, to go from 40 units to producing the 41st unit gives us a marginal cost of $45. Let's continue this problem. What is the cost of manufacturing 41 iPads? The marginal cost estimates C of A plus 1 minus C of A for any given A. We know our formula C prime of A is approximately equal to C of A plus 1 minus C of A. In this case, A equals 40, so we get C prime of 40 equals C of 41 minus C of 40. We already know the cost to produce 40 iPads is $5,000, and the marginal cost at 40, or the cost to produce the 41st iPad, is $45. By plugging in for C prime of 40 and C of 40, we get 45 equals C of 41 minus 5,000. This tells us the cost to produce 41 iPads is C of 41 is $5,045. Similarly, we have marginal revenue and marginal profit formulas. R prime of A is R of A plus 1 minus R of A, and P prime of A is approximately equal to P of A plus 1 minus P of A. Let's look at an example of marginal revenue. Given the revenue from producing and selling X iPads is R of X is 150X minus 0.01X squared in dollars, find the marginal revenue at a production level of 50 iPads. Notice we're not given points here, but we're given the actual function and want to find the marginal revenue. We can simply take the derivative to find it. R prime of X equals 150 minus 0.02X. And to find the marginal revenue at 50 iPads, we get R prime to 50 is 150 minus 0.02 times 50, which equals 149. This tells us the marginal revenue at 50 iPads is $149 per iPad. In other words, if we produce the 51st iPad, we'll generate another $149 in revenue. Continuing on, find the production levels where the revenue is 7,000. We'll start this by simply plugging in 7,000 for our revenue. 7,000 is 150x minus 0.01x squared. Note this is a quadratic function, so we'll bring all our terms to one side. This gives us 0.01x squared minus 150x plus 7,000 is 0. We'll now apply our quadratic formula. X equals negative b plus or minus square root of b squared minus 4ac all over 2a. We'll plug in for a, b, and c. This gives us two answers when we simplify. X equals 46.8 and 14,953.2. Please note we cannot produce 0.8 or 0.2 of an iPad, so we'll need to round. X equals 47 and X equals 14,953 are our two answers. That will give us this revenue.